So, yeah, just kind of looking at this thing here. I think it looks pretty good. I mean, your functional units to improve a single vector add instruction. Guess they did do something here. Status sets. Yeah, first thing, elements parallel. So they're vector register files, cellular registers, vector functional units, multi-lanes. So that's interesting. So you have like tens of operations back to back. If it's more important than latency. Not entirely sure about that, but yeah, if you have to sacrifice a little bit of latency to get more throughput, like much more throughput, that's probably fine. But yeah, I didn't really want too much latency either. VIS. Yeah, anyway. Damn, right now my brain's just kind of dying. Might have to come back to this later, but so I guess that's kind of your interior architecture with your multiple, like, 4-lane architecture. VRF, vector register file. Chaining. Oh. Fetch decode. Oh. Hmm. By the way, do they have a Zaymal? Interesting. So, okay, seems like all he does is kind of like a for loop. How many lanes you want, I guess, and that's kind of... Oh, damn, man, this fucking new GitHub thing is just so annoying. But you basically have your lanes. And then you have your kind of... 3. What's that? Okay. I don't know, but there's no comments either telling you what's happened, but it seems like, look, you're kind of going in and you're taking the start position and end position from the register of both of the operands. And you actually have your multiplier here that's multiplying 32-bit floats. So I think I get it. So you're kind of like what is it? Because the entire register itself is basically the thing. I guess that's in our arithmetic unit. Okay. Yeah, your A value reg, B value reg. It's kind of a bit trippy because the fields are defined as values inside the class. I guess they're public and scalar, but it does seem like it's almost a function kind of thing rather than an actual field. But I guess this is kind of like a self.aValueReg, and you're kind of extracting the array index of that value, and you're using the multiplier to multiply the thing, the A and B. And your results, I guess, your results are just this, I guess. And then you store that in your register, your result value register, and then you can kind of pipe that out to the output to IO register wire. Output wire. And it would probably work, I guess. Because that's probably one way to do it. Just have registers that store the entire thing. Then you use the kind of array indexing to retrieve the values at each index. And then multiply everything in sequence, and then kind of store everything. Well, store each kind of result, intermediate result, in results I, and in your results register. That stores it on the ith index of that wire register, I guess. I'm not sure exactly how that's kind of compiled down, so might have to look at exactly the block diagrams and stuff like that they generate VHDL. Execute dispatch GPU stage pipeline. Oh, okay. Text unit core. Do this. So your system Verilog, your inputs and outputs, your directives. If this happens, call this function. Otherwise, call this function, I guess. Your assignments, wiring and shit like that, I guess. Add cache, decache, pipeline. So your pipeline is kind of you can see like a lot of it includes kind of how the cache flows. A lot of the compute unit will pretty much just be the cache, I guess. FPU core, FPGA, square root, class CVT div. What do they have on this FPGA instruction? FMA. That begins. It's kind of where the code is, the logic is. I guess this is the clock edge positive. Only RAM is usually kind of both edges. So multiplication add, multiply add, sub, negation. I don't know what that is. ITOF. Is it OnlyFans? Is signed. Instruction FPU. Okay. And again, it's kind of like there's just a bunch of indirections as well, because then that's kind of like going to FPU. It's kind of do sub equals to 1. There's a lot of kind of crap going on. They have two kind of always blocks. The second block is kind of like the readout, I guess. I have no idea what they're trying to do here. So they're kind of setting the flags and outputs and stuff like that, I guess. Okay. That's just equal to 0. Local parameter. Wires. So generate begin FMA. Again, it seems like just more configuration code. I mean, function processing unit DPI. I mean, like, where's the actual core driver that's actually just doing, a 1+1 or a vector indexing plus vector indexing? Like here, maybe data FRM. Maybe this. I don't even know what FMA means either. They have one specifically for Altera. I guess that's what kind of and Stratera. Man. Well, that's kind of. Eh. Again, the defining things like shift registers, and here, I guess they're kind of just saying, look, you have the 32-bit register, you have your flags, enable these kind of input wires to fetch the data at this kind of position I on that lane, then kind of define a shift register if that's enabled, with your kind of parameters, clock reset lines, data in, data out, and then if that's not so that's only if if you're kind of simulating with Verilator. Otherwise, if you're kind of like compiling to FPGA or whatever, kind of as ASIC, you would create an ACL FDiv module that has your, kind of similar things, I guess. But I guess it's just this, but better. So you don't have to, because you can't simulate it, I guess. You don't need the extra stuff. That's true too. If you're using the shift register, you enable shift register. Okay, that's your floating point division, it seems. And again, I guess that's the actual module that does this. That does the thing. Maybe here. It's a declaration or what? What is this? Div. Multiplying unit, arithmetic unit. Loss. Yeah. Again, I mean, it's kind of declared there, but it's I don't see it being defined at all. I don't know what's going on. I guess it's just kind of like a data module that you could kind of pass around and retrieve from, maybe. Yeah, probably something like that. Well, that's kind of annoying. And you can see there's quite a lot of like just code that does stuff. I think reducer run was a bit better. Your RS-232 kind of protocol for the serial communications, I guess. Okay. bytecode encode heap x reg register file. So you kind of have to like specify the ticks directly, explicitly. As you can assign a port or something, one hot encoded, I guess. On index 0, you assign that to 1, etc. I guess. Reducer on. I'm looking for something about a vector. So your kind of top level reducer on value stack, reducer on state, signal dash top n to be mindful. Okay. 3 stacks value update case alternative heap encode memory. So you can see your usual kind of I/O ports. Significant number n. Signed I think. Bit. Register, reg file, code, heap, unistack, octostack. Oh, an octostack as well. Atom. Caching octostack. Top 8 elements are caching register to reduce propagation delay. So it seems like they already actually have quite a bit of a idea in mind on how to optimize things in that regard. I guess that's probably fine. Although I think it also introduces some complexity that you're going to have to deal with later on too. I would rather something that's just much simpler, much more kind of data oriented where possible. This isn't too bad, I guess. This is supposed to be specifically for graph reduction, which I guess that probably makes some kind of sense. And again, you know, your new reducer on function takes in a program, and I guess it executes that by doing like, okay, look, you know, is there anything interesting? You know, look, assigning this stuff in a do kind of monadic transforms, reg files, let du update check, nt, it's nt, new signed integer, I guess. New top, okay. da is dash, maybe dash top. Okay. Stack. What's a unistack again? Oh, okay. You take it in RAM algorithm, you kind of do your usual kind of stuff to set your push pop ports, I guess. I'm pretty sure this is lava, by the way, I think. Probably. Or maybe this is mostly lava. This is the kind of initialization. And at least the RAM algorithm here, you know, so this is a let that kind of, you know, defines a new top size out, new size. So that's kind of like your uni stack pushing and popping on a single element of type word m per clock cycle. That could be very fast, I guess. Per clock cycle, rather than, you know. I guess there was probably a pretty good reason why this was like quite a bit faster than, you know, an equivalent gigahertz level CPU on an FPGA that was like 95, 93 megahertz, I think. So it's pretty insane in my opinion. We don't really have too much to kind of compare with right now, so we can't really make too strong of a judgment, but I think it is, again, I think it really shows, though, that we really kind of probably converged onto a set of things that computing primitives and ideals that aren't the best that it could be, most efficient and stuff like that, I guess. Code memory application. Oh, okay. So this is kind of like, look, if you pop two arguments and then apply a function, I guess. Swap state. Again, yeah. IO primitive. So you set your IO write address based on if the write port is enabled, I guess, and you assign it to the arguments here. Okay. If inverse, what's that? Inventory, new top, 2, stack update. Okay, so you can see that's kind of where most of the stuff is probably done. Your actual primitive operation in your ALU, I guess. It's like an ALU dot primitive operation with these two arguments, specifically int values, I guess. Maybe that also just means bits rather than like ints per se, but LU. So yeah, you have your kind of function and your arguments. Pick G. If it's an add, then you add them here. Otherwise, you minus them. Is not equals, I think. Then you would compare them. Is that not equals? It seems like quite a bit of logic just for doing not equals. I mean, or is equals to f. Okay. Okay, so that's one way of like kind of doing is equals or is not equals at the same time, and you could, based on whatever the hell f actually is, then you can kind of reverse that, I guess, with this operator. Mic kind of turned off there. But yeah, I think it looks pretty good to me. Folding, unfolding, just essentially is template. Template, I think, is that just a function or combinator or something? Instruction. Oh, this tells you kind of like the reduction states: primitive, operation, swap, unwind, garbage collect, halt, unfold, etc. Instruction, argument, register, AP, AP, AP. Undeal as well. What the hell's undeal? So it takes an atom and returns a bit. That's the bytecode. That actually does the thing, I guess. Huh. Now you think about it, they have like bytecode, but then they also have like the plus operation, as we kind of just saw just then. So like maybe this is for something else. Template, like mostly templates and atoms and stuff like that. It kind of looks like pushing applications as well. Coding, make arguments, pointers. I don't know. I mean, caching octostack code. Store 32, load 32. So there's this encode. Encode. So I'm guessing they're trying to like have some kind of atomic FP32, and they're kind of trying to encode that, or what? Oh no, so I guess when they compare the plus, they're actually kind of they're actually using that prim add there. So this is the actual bytecode. That would actually kind of make sense then, I guess. So that's kind of like, your add, just shifting left again, adding and shifting. Is that how that's supposed to work? In 32, primitive, it takes a boolean s and returns an integer. Um. Hmm. Okay. Well, maybe we'll look at this later. So all this other stuff as well here. Registers, connections. They talk about vectors. I guess you could probably just have a vector of elements and then just apply your ALU stuff to it. That's probably just the easiest way. Technically, you would have a pretty simple vector register. Um, but yeah. Okay, I guess that's about it.